All right, so let's go through a few more of these little calculations, and you're working through these in your assignment. So this is our prototypical power law. We've got this continuous x. There's some scale, x min and x max. We'll call these cutoffs. I think you have A and B in your assignment. If gamma is not equal to 2, then you can see there's going to be an explosion here. Then this is what you get out. It's an integral, right? We're just going to put an x here and integrate from x min to x max, right? That's the mean of a given a probability distribution. And so the important thing here is that here's the exponent gamma, and the maximum cutoff and the min cutoff are just appearing here, right? That's it. There's no internal scale. There's no thing in between. If we had an exponential, for example, then the typical length scale of an exponential would be here. It's exactly right. It's the mean. So it's just the outsides, and all of these internal scales, they all kind of matter. None of them dominate. That's the really important thing. And so the mean blows up when you get to gamma equals 2. So that's as gamma, the way we framed it, right? It's x to the minus gamma. So as gamma is becoming smaller, then on a log-log plot, then the slope is becoming less, right? It's going out like this. It's a heavier tail, more stuff out here. So it makes sense that your average is getting bigger and bigger. And as soon as when we hit 2, then the mean becomes dominated by this maximum. And if we have no upper limit here, right, if we have an infinite, if x max is infinity, then the mean actually goes to infinity. All right, so it depends on the lower cutoff if gamma is greater than 2, right? So both of these things are involved. So when gamma is greater than 2, then this is a negative exponent. This is negative here. This thing is this x max is relatively large. This tends to be small. So this will be the dominant piece here. The signs will all work out. This is 2 minus a quantity greater than 2. So this is a negative quantity. This is negative. So we get something that, right, this is going to be a small piece. It's only going to depend on that lower cutoff, which is an end of it, right? So typical sample is small. Yes. When gamma is greater than 2, typical sample is large when it's less than 2. Right? This is just a feel for these things. Many real-world distributions, as we've talked about, are between 2 and 3. And that's where the exciting things, right, I've said these things. This is where the exciting things kind of appear, right? Right. Yes. Between 2 and 3. So in that case, the mean is going to be finite, or it depends on the lower cutoff. The variance is infinite, in quotes, right? It means that it's going to depend on the upper cutoff, which, large thing. It's going to be, potentially very, very large. So mostly in these cases, you're sampling things, you're getting small things most of the time, and then occasionally you get a big thing, and then even more occasionally you'll get a much bigger thing. So this is a bit of a dangerous situation. These are these wild distributions. So when gamma is greater than 3, then you've got a finite mean and a finite variance, and that tends to limit its threat, right? Dangerousness of this kind of distribution. And it still has infinite moments, right? For higher moments, they're infinite. But we're mostly going to be affected by the mean and variance of a distribution if we're sampling from it. Okay. So once you'll get a feel from this as you work through it all. It's very exciting. Right. So this is a piece to point out. So the variance is very helpful analytically. There are all sorts of variances add. This is a good thing. This is a nice feature. So we're going to use it. But potentially you'd want to actually start with this, right? What's the average that a value is? The average distance a value is away from the mean of your variable, right? That would be, and you might have mu here, for example. And that's just an absolute value, right? It's just the distance. That would be easier. So what we do instead is we put a square here, and then we take the square root, the root mean square. It has nice mathematical properties. This doesn't, right? This is a messy thing to work with, but it has different scalings if you do that, actually. So this is finite for this thing where the variance blows up. This is a finite quantity. Mean average deviation. It's not used that much because of math. Even though it's the sort of very basic, when you just say it, this is fair enough. Like, on average, how far away is our sample from the average? Like how, you know, and if it's just a delta distribution, then it's always there. It's really spread out. You know, this is going to characterize that nicely. We don't do it, but it does have different properties. It's important to say it. All right. Okay, so we're still going to focus on variance, of course. All right.